Okay. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. I just pray that you just bless this class, Lord. Help us to glorify you, Lord, in what we do. We thank you for your mercy to us each and every day, Lord. In your name I pray. Amen. All right, so last time I talked to you about what I would refer to typically as the integral with respect to arc length. So the integral with respect to arc length, so I'll state it up here just to have it as a point of contrast. We basically said the integral along a curve of a scalar function integrated with respect to arc length was the integral along the parameter domain, say a to b, f of gamma of t times the magnitude of the gamma dt, right? In other words, you take the function, you evaluate it at the parameterization of the curve, and then you multiply by the speed, and you integrate that over the domain of the parameterization of the path. Now here, of course, we had in mind the path goes from, say, gamma of A over to gamma of B, right? And this was the curve C. And so that's what we worked out an example or two, right? So today, we're going to discuss the next thing, which is the so-called the line integral of a vector field. All right, and so here's the definition. The integral, the line integral, along the curve C of f dot dr is equal to the integral from a to b of f of gamma of t dotted with d gamma dt. Now, admittedly, I'd rather express this setting gamma equal to r. This looks like the following. Integral from a to b of f of r of t dotted with dr dt. And somehow this seems like a better notation in this context, especially because it looks kind of like the definition is just dividing and multiplying by dt, which kind of isn't far from the truth. So this line integral of a vector field, what is it giving us? For a given vector field and a given curve, it gives us back some number. What does this number describe? I heard work. Okay. Let's see here. What do you guys know? Let's take it out for a spin. Let's think about work for a second. What do you guys know about work? You're like, plenty since I've been taking your class? Okay, fine, I'll accept it. How about work is equal to force times distance, right? This is like the 5th grade version of work, right? A little bit later, you learn that force is what? Work is what? It's a more grown-up version of that. How about it's the force dot the displacement? Now that assumes what? That assumes that the force is constant over the displacement, right? For example, if we had a force, say 10 newtons, right, applied to body moving from what? 100 in meters to 123 in meters along the line segment, right? You could calculate the work. What would the work be? It'd be the force Now, I got to tell you what direction the force is going, right? I told you vector equals 10 newtons. That's a problem, isn't it? What direction do you guys want to make it go? Backwards? Okay, I'll make that minus x hat then. There you go. So the force, so I would do force dot delta r, and the force minus 10 newtons, comma 0, comma 0. What's the displacement? Well, 1, 2, 3 minus 1, 0, 0, so it's 0, 2, 3 in meters. You take this dot product, what do you get? Oh, well, that's not very exciting.
0.
You get 0. Yay for backwards, yes. Now, why was that? It's because the force that's applied is perpendicular to the, right? I mean, if I drew a picture of this, we're going from, we're going from 1, 0, 0 to out here to 1, well, I can't draw it worth anything, but fine, 1, 2, 3, right, along this path. Oh man, what a horrible, along this path. Let me say that's where 1, 2, 3 is. And along the whole path, which I still haven't, I mean, these are both at x equals to 1, right? And so the force, it's always perpendicular to the motion, right? So perpendicular forces don't do work. But the thing is, this is very limiting, this kind of physics, because it has to assume that the force is the same along the whole displacement. Like the force can't be a function of position. So the next thing we teach you perhaps in Calculus 1, depending on who you have, blah, 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 is, well, if you have a one-dimensional force, right, you can talk about the work being the integral of f of x dx, right? I mean, that's the, for example, if the, that would be for a force which is variable in one direction. So you'd integrate from, from A to B, and that would give you the work done by F on A less than or equal to X less than or equal to B in a one-dimensional case, right? You might discuss that in, say, Calculus 1 or Calculus 2. It could happen. It may not have. If it didn't, it's no big deal. What happens when you put these two things together? You get this. So if we think about a curve, right? And if you think about a little displacement on the curve, you could call it dr, right? And so the little bit of work done as you go from, r to r plus dr, let's say. So suppose the initial point was r, so some coordinate system, There's some x, y, z coordinate system over here that we're doing things with respect to. So if we look at, some force applied to the motion of some physical body along this path, the curve C, if I have the force like this, then if I want the amount of work that's done in moving the particle from, say, r to r plus dr, I can say dw is simply f at the position r dotted with dr, because that's the displacement. A little change in position and the force at that position. Now, if it's an infinitesimal displacement, the force isn't changing much from r to r plus dr, right? So this is a very reasonable thing to write as the infinitesimal amount of work done going over that displacement, right? But how do you actually calculate this? Well, you write it in terms of a parameterization. So expressed in terms of parameters, this becomes, this equals, if you like, f of r of t dotted with dr dt times dt. And so then you integrate that over the appropriate time domain, and that gives you the total work done by the force along the curve. It's a combination of these two things. The dot product to pick up that the force has to be in the direction of motion, right, to do positive work, and the integration to take into account the fact that the force can be variable along the curve. There you go. That's just a motivation, though. The definition is as I stated it. And it's right that does calculate the work done by the force F along the curve C. What else does it do? Sometimes this is called the circulation of the vector field. So if you were to, if f was a velocity, if f was a velocity field, the velocity field of some liquid, then it is literally the case that f dot dr along the curve C calculates the circulation of the liquid along the curve. So in any event, this line integral, it calculates essentially how the vector field lines up with the curve. So let's see here. Let's look at an example. I'll do a really simple example to start with. So let's look at the vector field f of x, y, z equals to, let's say, what we got? The simplest example to do would be a constant, just a constant field. What if you have a constant, just a constant vector for your force field? What's the line integral give you? And so we integrate f dot dr, and let's look at some path. Let's see here, c. No relation to that c. Tell you what, let me make this a b, just so there's no confusion. That's a given constant vector. Okay, so then that would be the integral of b dot what? Dot dr dt from a to b. So here, of course, I have in mind some arbitrary curve from, r of a to r of b. Here's my curve C, right? Hey, we did this kind of integration earlier in the course, right? Remember? We've already talked about these sorts of integrals way earlier, before test 2, right? We did these kind of integrals before, a while ago. So I can pull the b out, right? I could, however we would do this, so this is basically b dot the integral of dr dt from a to b. But remember what the fundamental theorem of calculus said for such a thing? Yeah, that's r of b minus r of a by the fundamental theorem of calculus, part 2, for integrals of space curves. So what is that? Well, that's exactly b dot the displacement in r. In other words, it's the force dot the displacement. Check it out. It actually does, in fact, reproduce force dot displacement in the case of a constant vector field, like I would hope it would, because it's generalizing this idea. Yeah? Go on. All right. So another example, and I will give you another kind of boring example. So suppose my curve goes from, say, A0, 0 to B0, 0. All right. Here's my curve C. And I'm going to look at the vector field f of x, y, z just equal to, let's say, f of x, comma 0, comma 0. So what's the if I want to calculate the integral, the line integral of f dot dr, along this curve C. You see, in order to calculate the line integral, I have to understand what's the parameterization of the curve. This one was very forgiving. I didn't even need to get into details about the parameterization, except that it had endpoints, you know? Now this one is not, so this is much more specific. This curve is a line segment. How do you parameterize a line segment? So that's what's given. This is what we're trying to work out, right? Say again? What's the line segment?
A plus t times the vector b minus a, and then time value from...
You said AA plus t times b minus a? And then what for
0, 0.
0, 0? Do we, I think I agree. What were the time?
And then some sort of time value, like 0 is something else.
Let's see, 0 gets you what? A. How about time 1? B, right. Yeah, this is the standard, this is our go-to formula if we want to use time 0 to time 1 for our parameter. Yep.
Would it be easier to parameterize it just as RT equals T, comma 0, so your bounds equal to A and B?
You can also do that. Yeah, there's a couple different choices here, indeed. So basically, you're saying use x as the parameter and just let x go from A to B. You could do that too. That'd also be fine. I already wrote that, so I'll stick with it, but it's cool. This is the integral from 0 to 1. I mean, we do love integrating. I mean, integrating from 0 to 1 is ever so pleasant, though. I mean, it's hard to talk me out of that. And then let's see here. So you got f of x, 0, 0. That is, oh, sorry, but I don't have that, do I? Oh, yeah, now I see why I like Luke's idea better. I'm going to stick with it. So this is a plus t times, oh, man. Oh, I'm starting to like Luke's idea more in terms of less thinking, but it's okay. I'm going to stick with it. So dr dt is what? B minus a, right, 0, 0. Why did I write this? I'm using the definition of the line integral. You find a parameterization of the curve. You evaluate the vector field at the parameterization of the curve, at the path formula, right? You dot with the velocity and integrate over the parameter. This is the definition of the line integral. Okay, now what? Well, that's the integral from 0 to 1 of f of a plus t times b minus a times b minus a dt, at which point I will make a u equals to a plus t times b minus a substitution, which will give me that du is equal to b minus a times dt, which is ever so very convenient. It changes the bounds mysteriously from a to b, and then I get f of u du, which of course we could rewrite as the integral from a to b of f of x dx. Okay. Now we would have gotten to this immediately if we had used Luke's parameterization. But that was not a bad suggestion. It just was inconvenient for my example. But it's fine. Anyway, my point to you is what? This, again, is the thing you might have seen earlier in the calculus sequence. This is the work done by a force that's in one dimension in the x direction as you move the particle from x equals to a to x equals to b. You integrate from a to b, that gives you the work done. This notion of work is also contained in the general notion of work, all right? All right, so finally, let me actually do an actual real example for you, okay? I mean, these aren't fake examples. They're just not, they're kind of meta, aren't they? All right, so here's one. F of xyz equal to x squared comma y squared plus z comma 3. Find work done by f along two curves. Now here's the curves we're going to look at. We're going to go from the origin out to the point 1, 2, 3, all right, by the line segment, all right. But then we're also going to go from that point to that point by some other more complicated curve. You guys give me, here's your chance to be creative. We'll say C1 is the line segment, all right? I want to calculate the line integral among two different paths and see if they agree, see what happens, you know? So we'll do that one. All right, and this time, what's your name? I keep forgetting your name. I should know it by now. You've been in enough of my classes, I should remember. But so Ben's idea will be good for this one. In fact, I wouldn't want to use x as the parameter on this one. And then I need some other curve. Can you guys tell me something else that goes from the origin out there like that? I mean, it doesn't have to look like this exactly, but C2. So C1's a line segment. Let's say C2 is, how about x equals to t, a twisted cubic, y equals t squared, z equals t cubed. I like it. No, that's not going to quite work. And I'm going to be greedy. I want the time to go from 0 to 1. What do I have to do if I'm going to do that? What do I need to modify? Very good. Very good. There you go. Now we have a curve which goes from the origin to 1, 2, 3 as well. And it's not the line segment, right? These are genuinely different paths. Okay. So let's work it out. For C1, we have what? Let's say R1 of t is equal to, we got t, 2t, 3t, for 0 less than or equal to t less than or equal to 1. Is that a line? Is that a parameterization of a line? Yep. Does it go where it's supposed to, when it's supposed to? At time 0, it's at 0, right? At time 1, where is it? 1, 2, 3. Can I possibly be wrong? No. 2 points determine a line, right? Even in 3 dimensions. So I'm just saying, if you doubt me, don't doubt me. That's the line segment's parameterization. Okay. I mean, how do you find that? How did I come up with that? Yeah, I'm still using x as a parameter. I guess in Luke's defense, yeah, x is equal to t here. Fine. Got me. I'll prove Luke wrong soon enough. I will have my day. What's that? Yeah, yeah. Right. It does go back to the, I mean, generically speaking, if you want to go from a point P to a point Q, you can always fall back on our standard formula, which was that R of t is equal to P plus T times Q minus P, which is what Timothy's telling me, basically. It's just that P is 0 here, so you just take the displacement times T. But, yeah. Anyway, my point is this shouldn't be mysterious to you. You should know this. You should have complete confidence that you can parameterize a line segment between 2 points. I think everyone who's here probably can. People who are missing, though, those are the people I should be talking to. Maybe I am. Let's see here. I'm optimistic. All right, so dr1 dt is what? 1, 2, 3, right? All right, so those are the necessary ingredients. Now we can calculate the integral, the line integral along C1 of f dot dr. What do we do? So this is the integral from 0 to 1. And I'm going to write it symbolically for, no, I'm not. I'm just going to do it. What is f I will. Fine. You guys have got to stop talking. You're making me crazy. F of t, 2t, 3t, dotted with the RDT, which was 1, 2, 3. What does this mean? Let me put it in words. That means we put x equals to t, right? We put y is equal to 2t. We put z is equal to 3t into the formula for the vector field, right? We have to plug those into the given formula. So what is that? Yeah, I got a t squared, comma, y squared is 2t parentheses squared, right? Plus z. What is z? 3t, right? And then how do you evaluate 3 along the curve? It's just 3. Very good. You guys know how to take dot products, right? Indeed, you do. So we have to integrate from 0 to 1, t squared plus twice of 4t squared plus 3t plus 9. And let's see, in other words, integral from 0 to 1 of 9t squared plus 6t plus 9 dt, which is 3 plus 3 plus 9, which is 15. Does that make sense? I mean, what we did? All I'm doing is using the definition. That's all. So the work is 15 along that one. How about C2? C2, we have R2 of t is equal to t, 2t squared, 3t cubed. So dr2 dt is 1, 4t, 9t squared. Let's see, now I gotta face the music, right? I mean, integrate along C2, f dot dr, the line integral. What do I get? Integrate from 0 to 1 again. And I have to do f of t, 2t squared, 3t cubed, dotted with 1, 4t, 9t squared. All right, so what is that? So x is equal to t, right? So x squared is t squared. All right, next time I have to do y squared plus z. Y squared, well, y is now 2t squared, right? So y squared is 4t to the 4th plus z, but z is now 3t cubed. Now we have to evaluate the third component of the force field. This is the easy one. 3. Okay. Oops. And I still have to take the dot product with 4t, 9t squared, like so. All right. So what do we have? We have the integral from 0 to 1 of t squared plus 16t to the 5th plus 12t to the 4th plus 27t squared, which is a third plus 16 over 6 plus 12 over 5 plus 27 over 3, which is 9. I love integrating from 0 to 1 polynomials. It's fun. It's like relaxing. Oh man, what I don't love is adding those fractions. Come on. My calculator. Got no calculator. Looks like we're working in 30ths. 10 plus 5 times 16 is 90. 6 times 12 is 72 divided by, plus 270. Wait a minute, no. Oh, I leave the 9 over there by its lonesome. 30. What's that? Oh, it should be 80. Oh, yeah. Yeah, then I'd have 8 thirds, and then it'd be obvious that it's 80 30ths. Yeah. Anyway, what is that? 90, 162 over 30. Excuse me. Anyway, it's clear that this is not equal to 15, right? So it looks to me like we can say this much. If we calculate the work done by this vector field that we just made up here, x squared comma y squared plus z comma 3, if you calculate the work done by this force between a given pair of points along different paths with those same terminal points, you don't get the same work. Right? So it could be that that happens, which kind of makes sense, right? I mean, that's kind of our usual experience, right? If I take a chair in this classroom, right, and I push it from just to illustrate. Like you guys realize, the work it takes me to push the chair from here to here is not all the same as the work it takes me to push the chair like that, right? Clearly the second path required more work. Am I right? So we were familiar with this concept that work should be path dependent. I don't know.
Actually, for the third it goes it's 14.4.
Oh, there's no classroom down there. It's just a physics lab. At best, I messed up a physics lab. What's that?
It's 14.4.
Ah, 14.4. Uh-huh. Oh, well, interesting. Yeah. All right, so a force field, all right, which has the property that if you calculate the work done between a given pair of points, and if the work done is independent of the path you choose between that given pair of points, that force field is said to have path independence. All right, it's a property of vector fields. You can say of a path independent field. Was there a question?
Yeah, maybe that's what it was. Most of the situations I thought it didn't matter what path you took, you'd still end up with the same change in energy. That's what I was trying to reconcile those.
Right. So that's exactly where we're headed. We want to understand why it is in physics sometimes the path didn't matter. When is that the case? Why is that the case, right? Excuse me. If you're keeping score, we now have two definitions, right? Types of vector fields. What do we have so far? Right, we had conservative. Conservative vector field F means that there exists some function f such that what? The vector field is the gradient of that potential function f. And now 2, I have path independent. F is path independent. If you look at any 2 points, say from P to Q, if you look at any 2 curves, C1, C2, right? The integral along C1 of f dot dr is equal to the integral along C2 of f dot dr. Okay. Just collecting my thoughts. Let's do some more examples of line integrals. I actually want to now introduce. What did we prove already with this though? Just to remind myself. What was the other thing we had? 3. We could have had that the. I would make this 4 in my list in the notes. So I have this is that the if the curl of f, right, is not equal to 0, that implies that f is not equal to the gradient of f, right? Because we have an identity, which is that the curl of the gradient of f is equal to 0, right? And I told you that, in fact, we'll eventually prove that this arrow goes both ways, in the sense that we'll eventually get the statement that f is equal to the gradient of f if and only if f is if and only if the curl of f is equal to 0. But there's some extra fine print on there, topological fine print. Okay. There's one other thing in this list while I'm at it, which is that you could talk about f integrating around loops to be 0. So like the integral around a loop of f dot dr is equal to 0. So in fact, one of the theorems we're going to prove in not too long is that this list of 4 things are in fact, there are 4 equivalent characterizations of a vector field. In fact, these are the same thing. But all in good time. I probably wouldn't have said that if Luke hadn't said what he said. All right. I think we're done with this. You can check, by the way, the curl of that vector field is not 0. I invite you to check the curl of this f. It picks up a non-trivial piece from this z right here. So this f I could rewrite as the gradient of, looks to me like 1/2 x squared, 1/3 x cubed, plus 1/3 y cubed, plus 3z, plus the vector field 0, z, 0. That piece is the potential, it is conservative. That part of f is conservative. You can easily calculate that the gradient of what I wrote just there gives you back everything in the force field except for the z term. Do you agree? But the z term, if you calculate the curl of 0, z, 0, you get, this is probably easier to look at explicitly in terms of You get z hat partial z cross z hat, excuse me, cross zy hat, which gives me z. It gives me, I believe the curl works out to 1 times z hat cross y hat, which is what? Oh, excuse me. So I do believe the curl of f is minus x hat, if you work it out. Es bueno? Okay. Now, you engineers don't usually like the notation I'm using right here. There is another notation very popular for line integrals. Let me show it to you. The so-called differential notation. All right, and it's simply this. If I have f, well, I'll just define it. If I have the integral along a curve of p dx, what that is the integral from, say, a to b. You take p, you evaluate it at the parameterization of the curve, and then you multiply by the dx dt and times dt. So here, I'm using the notation r is equal to x, y, z, okay? And what do you think the integral of over c of q dy would be? Integral over c of r dz. What happens if you add these together? So you put these gadgets together. If we have the integral of p dx plus q dy plus r dz over c, adding these in the natural way gives me the following: integral from a to b of p of r of t dx dt plus q of r of t dy dt plus r of r of t, so much writing, dz dt, big parentheses, dt, I feel like one of those ninja warriors. After the cliffhanger or whatever, you got to hang upside down and shake out the arms, you know. It's not exactly a good analogy, but I don't think I'd last long on that show. Here. I'm pretty sure it's the reason that my son was climbing the walls last year, though. He got so he does this spider climb between the hallway, just and then he just climb upwards because the hallway's narrow enough. We have since banned it because he fell onto a door frame and cut his hand open. It's not good. Don't let kids climb walls. It should be not allowed. Yeah.
So when you walk down a path, do you stop and take the integral of the short distance?
Me? Do I try to optimize? Not personally. No, I just walk. Yeah.
You don't use it? You don't stop and wait. This one has less work.
Well, I mean, I'm always trying to find the path of least work. That's true. I do that. That's true. Oh. Now, this is I'm just omitting the R of t dependence here. Excuse, I hope you could forgive me. Thank you. And so what do you have? You have the integral from a to b of f of r of t dot the r dt, which is the line integral. So you can use differential notation to calculate the line integral because this is an identity. Now the differential notation is a little bit easier. Let me kind of like show you how that goes. It's just really just a mnemonic to remember how to do line integrals. I think it's important to see the definition I gave you first because it shows you geometrically exactly what the line integral is. Well, there's a little bit more I could say about that, and I will. But first I'm going to show you this differential thing. Let's do a two-dimensional one. One of my favorite examples. Let's integrate over the counterclockwise oriented unit circle. And we're going to calculate the, let's see here. The vector field will be minus y comma x dot dr. Now, you typically would see this written like the following. So this integral with circle just means it's the integral around a loop. It just tells you it's integral around a loop. And the arrow is pretty nice because it tells you the orientation counterclockwise. So again, x squared plus y squared equals to 1. But in differential notation, this is just what? Minus y dx plus x dy. So to calculate this line integral, all I have to do is parameterize x and y for the circle. How about this? X is equal to our cosine theta. Well, x is equal to what? Cosine theta, right? Y is equal to sine theta, because I'm looking at a unit circle, counterclockwise oriented, right? So what's dx? What's dy? Sine theta d theta, right? Cosine theta d theta. And you can literally plug those up in here, and that's the line integral. Minus y was minus sine theta. Dx was minus sine theta d theta plus cosine theta d theta. Yep. That's just a notation that says the integral's around a loop. I could also write it without the circle. I'm just showing you.
So is the fact that that equals the circumference just coincidence?
Like suppose you have a friend named Bill, and he's really dumb. You could refer to him as Stupid Bill. Or sometimes you could just refer to him as Bill. It's kind of up to you. The circle is like saying stupid. Except it's not stupid. It's actually a really cool notation. It's like that, though.
You ever consider being a counselor?
A counselor? I have only one piece of advice. Take math. What should I make my major be? That's easy. Math. What's the best major to choose here? That's easy. Math. Should I be a psychology major? No. You can work at McDonald's without going to school here. That's fine. Oh, I'm sorry. Did I say that? I'm not supposed to say that. Oops, I'm sorry. You can also work at McDonald's with a math major. Don't get me wrong. All right, anyway, it's up to you. There was a point to this. Oh, could this be a conservative vector field? Why is this interchangeable? Why is path independent interchangeable with integral around loop is 0? Let's look at that for a second. So connection, let's say connection of items 2 and 3. Sorry, I'm trying to break up the monotony of just showing you examples with actual theoretical tidbits. So in other words, let's assume, which one do you want to start with? Do you want to assume path independence? Let's assume f is path independent, okay? Assume f is path independent. What I want to show you is that that implies that the integral around a loop for f has to be 0. So pick a loop, any loop. Let's say L. I don't know. Here you go. Here's L. I mean, it doesn't have to be a circle. A loop can look all kinds of like, I mean, a loop could look like this. It could be like, still a loop. A loop is just a closed curve that doesn't have a self-intersection, right? So you pick 2 points. Pick any 2 points you like on this loop, all right? So pick 2 points. P and Q, right? So, and the loop, I need to pick an orientation for the loop. So let's suppose the loop was oriented, what do you guys want? Clockwise, counterclockwise? Up to you, I don't care. Counterclockwise, all right. What? Counter. This way. So if you look at this loop, right, it's actually 2 curves put together, isn't it? Like, on the one hand, you've got this top loop. Why did I make this so complicated? What's wrong with me? This one, right, which we could call C1. And then on the other side, you've got, going the other way, like that, C2, right? And you can see that L is equal to, what is it? It's C1 union C2, right? You hopefully won't be surprised to hear me tell you that if we integrate the vector field, right, dr, we calculate the line integral of the vector field along L, right, we can break that up as the integral along C1 plus the integral along C2, right? Because if the way this integral is constructive, it's additive. So if you take different paths and join them together to get the integral, get the work done by the total path, you just add the work done on each subpath and add them together. So I mean, the integral has this additivity like this. You'll forgive me if I don't formally prove that. I mean, I could formally prove this for you, but I think it's clear enough that that's what should be happening for the definition, right? The proof would be little more of the corresponding proof for calculus 1. Yep. My point is, if any loop you pick, you can automatically divide it into 2 paths, right? But what else can we say is that one path it's not the reversal of the other path, but it's like path in my current notation, C2 goes from P to Q, right? C1 goes from Q to P. So if I reverse C1, oh, I see now I forgot to prove something today. I'll have to get out the projector here in a minute. I forgot to prove for you that what happens if we reparameterize, right? I gave you a definition for the line integral in terms of a path, and I didn't discuss what happens if we choose a different path. I did that for the scalar integral yesterday, though, which is different. This is a different integral. But the question is, what would that corresponding argument look like for the line integral we covered today? The answer is almost the same, except that there's no absolute value bar. So if you change the orientation of the curve, it ends up changing the sign of the line integral. In other words, the work going from P to Q is minus the work going from Q to P for the same path. If you reverse the curve, you reverse the sign of the work. Anyway, so to be fair, I have to put minus a minus here for the reversal, and there you have it. So this then, that, but, so these are what? These are equal by path independence. Why is that? Because C1 and C2, minus C1 and C2 are both paths that have the same starting and ending points. So by path independence, the work done is the same. The line integral is the same. Hence, this is equal to 0. It's not really that hard to see how to reverse this argument. What if you assumed that 3 was true? How would you get that 2 is true? Assume a loop is 0, right? But you can take any loop. I mean, if you take any two paths between 2 points, right, you just reverse one of the paths, and then you got a loop. So by almost the same argument, you can prove the reverse implication. You see what I'm saying? The other direction for this argument, if we assume the integral around loop of f dot dr is equal to 0, then if I take two paths, right, like this, I can easily convert those to a loop, right? What's the loop that's formed from C1 and C2? How about C1 union minus C2? That's a loop. So the integral around that loop is assumed to be 0, but then you can break it up into the integral over C1 plus the integral over minus C2 is equal to 0, but then you move to the other side and pull the minus out, you get equality of C1 and C2, so you get path independence. So integral around loop being 0 and path independence are equivalent. Yeah.
In your top example, is it just coincidence that you got Mr. Tyler within your circle?
No, I don't think so. If we did this for a circle of radius r, what would happen? It's for a good cause. Here. If I put it, let's see here, if you'll allow me to edit that example. So we put an r here, an r here, that puts an r here, that puts an r here. Oh, so sorry. Looks like you got an r squared. So yes, it is coincidental. But you see, this is non-zero, right? So the integral around a loop is not 0. What does that say about? So f of xy equals to minus y comma x is not conservative on the plane. Well, all right. All right, so let's connect with yesterday. How can we rewrite the line integral in terms of, how can we rewrite this integral in terms of the scalar integral? What would you do? What's the difference between what we're doing and what we did yesterday? We're integrating a vector field, right? So if we look at the integral of f dot dr along a curve C. So let's talk about the connection with integral with respect to arc length. And this is also a good calculation to look at because it again will confirm what I have claimed today about the geometric meaning of the line integral. All right, so here it is. This is, again, the integral from a to b of f of r of t